We will continue with our discussion of thin airfoil theory. Quickly to recap, an airfoil is composed of a chord line, and we define a camber line about it. Then we add equal amount of thickness above and below. Then the airfoil is placed at an angle of attack where the free stream has got a finite angle alpha relative to the chord line, which is the straight line in this picture here. So we said we are going to neglect the thickness effect because in our previous studies on building block effects, sources, sinks, even doublets did not add any lift because they disturb the flow equally above and below. Therefore, we neglect the thickness effect, so we study flow over a foil. So this is like what we call the camber line shape. By the way, this distance is 2 to 4%. It's not very far. So later on, we're going to make additional approximations taking advantage of it. Nevertheless, this is an approximation, so it's an approximate theory which totally neglects the thickness effects. If you want to include the thickness effects, there is indeed a theory called a panel method, which is what we would cover in a later video. Continuing with what we have already covered, we said that the camber line is defined as a function z of x. Free stream is like this way, this purple line, the x-axis is parallel to the x-axis. The slope at any point is dz dx. It's a very, very small number because the camber line is only 2 to 3% above the chord line. If this is 1 meter, this maximum height is 2% to 4%. That means 2 centimeter, 4 centimeter, very, very small. We decided to rotate this whole picture in the clockwise direction so that the free stream became parallel to the x-axis like in a wind tunnel. Then the slope will, every line or every degree of slope will decrease by that 1 degree or 2 degree depending on how much you rotate. So if you rotate it by alpha, then the new slope will be the original slope dz dx minus alpha. So the flow is tangent to the body surface, we said. Therefore w over u, where w is the velocity in the vertical direction, u is the velocity in the horizontal direction, is this slope. Alpha, by the way, is in radians. This is a non-dimensional number. So this whole thing is non-dimensional. This is non-dimensional. We made another assumption that because the body is so thin, camber line is all we have left. It's 1 or 2% away from the chord line. And because the angle of attack is very small, 5 to 10 degrees, radian, 0.1, 0.2 is a lot. Okay. Because the number is small, the u component of velocity is dominated by the free stream component of velocity, which is hundreds of meters per second, plus small amount of disturbances, which is like tens of meters per second. So we neglect the disturbance velocity in preference to the free stream velocity. Therefore, we approximate this u by v infinity. That's why this exact boundary condition became this approximate boundary condition. So this is the boundary condition that applies on the camber line. Now, we had to choose the building block. We said we need free stream. Kutajukovsky theorem says rho times v infinity times gamma. So free stream is important. Gamma is important. That means vortices are important. Sources, sinks, doublet, they didn't add any lift. They equally disturb the flow above and below. Therefore, they are not needed. So we're going to take some vorticity distributed all over the camber line. So what we have to normally do is that we are going to divide the camber line into small slices of length delta c. Then on each slice, we'll put the vorticity d gamma of strength gamma c times dc. We write it this way because gamma has got a units of distance times velocity. So this is distance, this is velocity. What is the physical meaning of this d gamma? Where is the circulation residing? It's in the boundary layer above the camber line and below the camber line. So if you put a box around it, that's all the vorticity inside that box of length delta c. Now, because this is only 1 or 2% above, maybe very, very mild camber, rather than putting these vortices on this red line itself, which is the way it should be viewed, we are approximately putting it right on the blue line because this is much easier to integrate. After all, this red line is only 1 or 2% above or 1 or 2% below the blue line. So small deviations. So within the framework of our quote unquote small disturbance theory or a small perturbation theory, we can approximate the vorticity distribution over the red line by an equivalent vorticity distribution on the blue line, which is the chord line. So we chop up the chord line into tiny segments of width delta xc, and then over this, within this line, you have this much amount of circulation that is originally on the upper surface and lower surface boundary layers. We have just dumped it here or lumped it here. It's got units of velocity times distance. This is my original point P, so the flow has to be tangent to the surface. The linearized boundary condition we have developed earlier. So this is the velocity W based on the slope, angle of attack, and free stream velocity. All right. Now we are going to locate the point P at X, whereas we're going to call this segment C, just to keep these two things honest and separate. We can't call everything X because we won't know where is this lumped vortex of the strength delta gamma, or where is this point P. So this is located at X, this is located at C, measured always from the leading edge, from 0 to chord. Okay, X goes from 0 to X equal to chord. Remember, the chord line is along this line. So the chord is actually this distance, but again within the small angle of attack approximation, chord times cosine of alpha is roughly chord, because alpha is very small. Therefore, this distance is called chord rather than the original definition from the leading edge of the camber line to the trailing edge of the camber line. Okay, so this is the point P. These are our distributed vortices. This is dxc. So I have a clockwise vortex here. It's spinning clockwise. The distance between this vortex and this point P is c minus x. So this is the distance. Then we have a building block solution that says the velocity is 1 over 2 pi times gamma over 2 pi r, where r is a radial distance. Go back to the building block solution. So here r, the radial distance, is the distance between the vortex and the point. So the distance is c minus x. So this is dw. This is just due to this little vorticity just over this small slice of the chord line. To get this expression, we have to go back to our building block solution slides. You would see we had developed v theta equal to gamma over 2 pi r. So a vortex will produce a circular streamline pattern. So the velocity surrounding the vortex will be gamma over 2 pi r. So when you integrate 2 pi r times r d theta, 1 over gamma over 2 pi r times r d theta, integrate around a circle, you'll get back the circulation of gamma. Again from the previous set of slides. Now to get the W, all you have to do is integrate it from the leading edge from x equal to 0 all the way to x equal to c. Therefore, W is the integral of this expression from 0 to c. So applying the boundary condition, we developed approximate boundary condition, W equal to V infinity times dz over dx minus alpha equal to this quantity. So this is the equation that we need to solve. This is a Fredholm integral equation of the first kind. We call it an integral equation because the unknown is buried inside the integral. It's not a ODE, it's not a PDE, it's unfortunately it's an integral equation. So the thin airfoil theory developers, primarily in Germany, they had to work with this. They didn't have computers, so they had to analytically solve it, not even numerically. So they came up with very clever ways of solving it, integrating it. So that's what we are going to be looking at it in this particular set of videos on thin airfoil theory. So the common practice is you assume a solution, integrate it, and see if it satisfies the boundary condition. We start with calculus 101. Yes, we can assume a series solution for gamma, or a Taylor series or a polynomial solution, integrate it. but it's very hard to integrate xi over xi minus x, xi squared over xi minus x, and so forth. So these people, they said, we are going to change a variable, come up with something different. Instead of distances, I'm going to convert them into angles. Then I'm going to use what we call a Fourier series upon the top instead of a Taylor series or a polynomial series. How did they know Fourier series? Trial and error. Lots of trial, lots of different functions, lots of different change of variables. When you took Calc 1 in an exam, when they gave you an integral, you tried a change of variable. The first thing may not have worked, then you tried something else, until you got the answer or until the time ran out. So in this case, that's what they did. They looked at several change of variables to come up with a way of analytically integrating this particular thing. It turned out a Fourier series that we will describe was the one that was the most successful. So that's what we are going to be using in our work. So the change of variable they did was they said, I'm going to change the distance xi that goes from the leading edge of the airfoil to trailing edge to xi. So xi goes from 0 to 1. That means the 1 minus cosine theta must go from 0 to 1. If theta is 0, cosine theta is 1. So 1 minus 1 is 0. So theta equal to 0 represents the leading edge. If you put theta equal to pi, cosine of pi is minus 1. Cosine of 180 degrees is minus 1. We already have a minus here, so that becomes a plus 1. 1 plus 1 is 2. 2 divided by 2 is 1. So xi becomes equal to chord. So xi goes from 0 to c when theta goes from 0 to pi. So this is the change of variable that stuck. Okay, they tried many other changes, I'm sure. Lots of beer, lots of scratching their head. Many of them have no hair if you see their pictures. So this is xi. In the previous integral, there is a dxi. So all you have to do is take a differential of this that produces c over 2. This becomes minus of sine theta. There is a minus here, so it becomes plus of sine theta d theta. How about x? Same variable variation, except we have theta is a variable, so this is a fixed point. So I'm going to call theta naught some fixed angle that represents x. So if somebody gives me x and c, I can always solve for theta naught. For example, let's say x was pi over 2. That means x of x is c over 2. Then this should be 1 minus cosine theta must be equal to 1. That means cosine theta naught should be 0. That means theta naught must be pi over 2. So I can always solve for theta naught if I know where that point P is located, where I'm applying the boundary condition. Then they assumed a series for gamma. It had some fixed component plus a Fourier series. Okay. I'm going to explain the Fourier series here. It goes from n equal to 1 all the way to infinity. That means there are an infinite number of terms, but if it's converging, that means each and every term is hopefully smaller than the other. A1, A2, A3, A4, if you add it, it becomes smaller and smaller. Eventually, A infinity is very small, negligible. In fact, we are going to truncate it to 1 or 2 or 3 terms. It turns out we only need A0, A1, and A2. Everything else is not needed in our theory, as we will see later. What if you pick sine n theta, why not cosine of n theta? Because if you use cosine of n theta, remember theta goes from 0 to pi. So theta equal to pi is at the trailing edge. Cosine of pi is non-zero. That means the vorticity is going to be non-zero at the trailing edge. We know Coulomb condition says things should be going smoothly at the trailing edge. That means there should be no vortex at the trailing edge. Otherwise, the flow will go around the trailing edge. Okay. So if there's a vortex here, it will push the flow this way. If it is a counterclockwise vortex, if it's a clockwise vortex, it will push it this way. So right at the trailing edge, circularly this vortex d gamma must go to 0. That means this gamma xi should go to 0. The only way we can ensure it is by using sine functions, because cosine of 0 is not 0, cosine of 2 times cosine of pi is not 0, cosine of 2 pi is not 0, cosine of n pi is not 0. Therefore, they said, on the other hand, sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0, sine of n pi is 0, the trailing edge. That's why they picked the Fourier series, including only the sine theta terms. How about this is a leading term? It looks singular because right at the leading edge, when theta goes to 0, this seems to go to infinity. So there is a singularity at the leading edge, but it's an integral singularity. How about at the trailing edge? Theta goes to pi, this is 0. Here cosine theta goes to -1, so this is 0, 0 over 0. So if you use a L'Hopital rule, you could show that this goes to 0, satisfying the Coulomb condition. So gamma theta is 0 at the trailing edge. Okay, at theta equal to pi. Okay. So here is a L'Hopital rule, or you could say 1 plus cosine theta is 2 cosine square theta over 2. Sine theta is 2 tan theta over 2 cosine theta over 2. Therefore, the first term will become just cosine theta over 2 times sine theta over 2. If you put theta equal to pi, this will become 1, this will become 0. Therefore, this term goes to 0 at the trailing edge. So, Coulomb condition is satisfied. So, this is the series that they decided to use. So, we will stop this part of the video at this point and continue with the next video.